Before we get there, we need to insert a discussion on formal algorithm analysis, algorithms and algorithm analysis. And to give you a motivating example of why this is important, I've already shown you a few examples with lists, and I'm going to revisit this one that we've looked at before, where there's where you're just trying to sum up a bunch of numbers. What I've got here is a setup where there's 1 million elements here. We randomly generate 1 million elements. And then we start the system time here and end the system time, and in between, we're actually summing those up. And initially, I'm going to use an array-based list. And when I do this, it only takes, 0.009 seconds. Even if I bump this up from 1 million to 10 million, right, then we would expect it to still only take about a little bit more time, right? 10 times as big. It wasn't 10 times as slow, but it was, the same similar order of magnitude. Where, on the other hand, let me go ahead and start out with 100,000 and use a linked list instead. Right? Let me go ahead and run this, and it's still going, by the way, even with just 100,000. That took 4 seconds. Okay, so if I go up from 100,000 to 1 million, let me go ahead and start it. Give me a quick estimate here. How long is this going to take? I'll let it run while you're making your guess. Is it 10 times as long? So I think it was 4 seconds before. Should it be 40 seconds now? Because 100,000 up to 1 million, that's 10 times as big? Or what? Well, let's think about it. I'll let it run. Maybe we'll get an answer here. I'm going to go ahead and change over here to a projector. Let's see. To the .cam. There we go. All right. Now, let's think about what's going on here. When I switched over to a linked list, okay, hopefully this will autofocus. So let's just take a small example here. I've got 1, 2, 3, 4, 5 things in this, 10, 20, 30, 40, and 50. How many operations am I going to be performing in order to sum the first element, the second element, the third element, the fourth element, the fifth element, right? Now remember, the way that this is working is you can't just jump to the fifth element or the third element or whatever, right? In a linked list, you have to start at the head, and then you have to traverse the nodes. Now to get to the first one, do I do any node traversals? No, I'm right there. But I do one addition, right? Now to get to the second node, I have to start at the first one, so I start at the second one, then I go to the next one, so that's one node traversal, and then still only one addition, right? So for the third one, at index 2, I have to do 2 node traversals, and then one more addition. For the fourth one, at index 3, 1, 2, 3 node traversals, and one addition, and you can start to see the pattern here, 4 and then 1. So now I'm doing all these operations. There are probably other operations that I'm doing in a computer. If you are actually going to go ahead and compile this down to the machine level, there are lots of different things that are going on. You're loading up a memory address into a register. Then you're making, you're determining whether or not this is equal, and then you're making a jump, right? Are you at the end of your list or not, right? So you're doing a lot of operations, but these are the 2 I want to focus on for now. How many total operations am I doing, right? If I sum these up, this is 1 plus 2 plus 3 plus 4. What is that going to be? 10. And number of additions, 5 total, right? So which one of these things should I be focusing on? If I only wanted to focus on one or the other, which one should I focus on? Node traversals. Why? Why should I focus on this node traversals over here rather than all these additions? This is what I'm actually doing, right? I'm just summing these up. Why is this maybe more important? I'm doing more of them, right? And if I'm doing more of them, then maybe this is the more expensive operation here, okay? So already we're looking at different operations in a computer, different operations in an algorithm. Maybe one measure of what we should be looking at is the most common operation, right? All right. Then let's think about this. And I can't see it right now, so I don't know if it's still running or not. We'll find out in a second here. Let me go ahead and generalize this. Suppose that I didn't have just 5 nodes in this linked list. Suppose I had ... I had n of them. There are n nodes here. And when I'm talking about n is going to be very large. Like the one that I'm running right now is 1 million, right? With n being 1 million. But I don't want to just know the answer for 1 million, which I'm going to show you in a second here if it actually executes. I don't want to know the answer for how long this is going to take for 100,000 or even 10 million. Right? I want to know, in terms of n, how many operations am I actually going to do here? Well, to get to, for the first element, for element I, for I running from 0, right, index 0, then 1, then 2, ... You saw the pattern before, right? If you want to get to element I at index I, how many node traversals did you have to do? You had to do I of them. So number of traversals is going to be 0, 1, 2. And when will this algorithm be done executing? When is it summing everything up? At n minus 1, right? Remember, because we start at 0. So ... n minus 1. What's the total here? If I sum all of these up, 1 plus, or 0, you can ignore that, right? 0 doesn't contribute anything to a sum. 1 plus 2 plus 3 plus 4, all the way up to n minus 1, right? That's the number of node traversals that I'll end up doing for this algorithm right here. So number of total node traversals is going to be a summation of I running from, now I'm going to start it at 1, because, again, 0 doesn't sum up anything, up to n minus 1 of I, right? Again, this is 1 plus 2 plus 3 plus ... plus n minus 1 as your last one. Does this look familiar to anybody? It's, well, what is this thing called right here? It's a summation. It's not an infinite series. You can call it a series if you want to, but it's just a summation. 1 plus 2 plus 3 plus 4. Does anybody know how you can get a closed form solution of this? Usually you look at this as like the prime example for induction in, say, 235 or something. So it's going to be simply, in this case, since I'm only going up to n minus 1, it's going to be n times, or n minus 1 times n minus 1 plus 1, so those will cancel, and I'll have something like this, right? So I'll go ahead and simplify this. 1/2 n squared minus n over 2. Well, one half n, right? Something like that, okay? So if I'm going to do this with 1 million elements, then if I plug in n, or 1 million for n, then I'm going to get 100 million squared times 1/2 minus 500,000 operations, right? You can pull out your calculator and do however many of those operations are. But what I want to focus on instead is, what's the most important term here? If I go from 100,000 elements to 1 million elements to 10 million elements, which one of these terms is going to grow the fastest? The square, right? All right, so let me go ahead and just chop that off. Forget about it for now, all right? Now looking at only at 1/2 n squared, at the end of the day, is that 1/2 really all that important? If I want to look at the growth rate of the function, it's just a constant sitting out front. So let me go ahead and get rid of that as well. And by the way, the constants are important if you want to look at some things from an empirical point of view. But guess what happens to the constant when you go from a computer that is x fast to a computer that is 2x fast? In other words, twice as fast. You upgrade your hardware. You upgrade your, you modify your software to be twice as fast, right? Guess what happens to this constant out front? It goes down, because each operation takes less time, right? You can do more operations in the same amount of time. So I don't want to look at today's computers. I don't want to look at, would it be a good measure to look at the performance of an algorithm based on computers' performance in the 80s? No. So I don't want to do that. I want to look at performance going forward. And the performance going forward is captured by this term, n squared. As you go for larger and larger list sizes, right, linked list sizes, then the number of operations that you're going to be performing is going to grow with respect to this term. Let's put that into perspective. If I say n squared, right, and I go say, so it's going to grow with respect to n squared. If I go from 1 million elements to 10 million elements, I'm increasing the input size tenfold, right? If I'm going from n to 10n, right, the input size, then what is the performance? In other words, what is the number of operations that you'll actually be performing? It goes from n squared, because we've already observed that that's what it is, right, to what? All I need to do is take this 10n and plug it in for n down here. And it's 10n all squared, okay? Which is equal to 100 n squared, right? Because you just take the square and you distribute it to both there. So in other words, what's the interpretation here? If I double the input, or if, not doubling, but if I go a 10 times growth in input leads to, what's the constant out front here now? 100 times more operations, right? And if you have 100 times more operations, this is 100 times slower, right? 100 times more time for you to actually execute something. Hopefully, okay, it didn't go to sleep entirely. Let's see if it's done. Well, actually, before we look at it, before I even look at it, I went from 100,000 to 1 million. 100,000 took, what was it, 4 seconds? All right. So if I've got 100 times slower, this should take about 400 seconds, thereabouts. 400 seconds is 4 minutes and some change, right? Let's find out if our estimate, our guesstimate there is right. Desk HTML. All right. Oh, wow. Really close, right? There's a little bit more than that, but that's because my computer is doing other things in the background. 409 seconds, right? So it almost took 8 minutes or so, a little less than 8 minutes. Okay, let's go back to an array list. And again, this was 1 million. Did it take 500 seconds? In other words, almost 10 minutes to execute this when I used an array list? No. It took vastly less time to do this, right? And to do this properly, you'd want to run it over and over again in isolation, take an average, and then do stuff. And I already did that for you. I'm going to show that to you in a second here. So why is this, right? Well, we've already seen that a linked list means that you have to, with an array-based list, you can jump to a memory offset. In other words, if I did the same analysis that we did up here with an array-based list, it's only going to be linear. I'm going to be doing, if I have a million elements, then I'm doing a million summations, and I'm doing a million retrieval operations, because I can immediately jump there. I don't have to start at the beginning and traverse through the list until I get to what I'm looking for, right? So an array-based list gave me the advantage that I have random access and I can jump to it immediately. It didn't cost me anything to get an element. Or it cost me something, but not as much as it cost me for a linked list. A linked list, you have to traverse the entire thing, right? And so, consequently, an array-based list is a constant operation. It has the same cost regardless of the index that you're trying to jump to. But a linked list has a linear cost. A linked list has a linear cost to retrieve an element at index I. Right? And for that reason, we've got a vastly different performance for even moderately large values of our list. Right? By the way, 1 million elements, 10 million elements, this is not big data. That's nothing. Right? Real big data would be what they're handling over in the Holland Computing Center. They're handling petabytes of data. This is not even gigabytes of data. 100 or 10 million integers, that's 40 million bytes. That's less than 40 megs, right? That is in today's day and age, that's nowhere near big data. 50 years ago, that was big data, right? Astronomical data 50 years ago, right? Just so that you have it in the notes here, I'll go ahead and make sure that you've got that that example. Now let's look at it from a more formal point of view. Again, with an array-based list, each get function, get sub I, call takes a constant amount of time, right? Therefore, the for loop executes n times, right? Remember, we're wanting to keep it general, not just 10 million, 100,000, or 1 million. I want to look at it from the perspective of n, where n is the number of things in my list, right? The total amount of time taken is proportional to n, right? Well, n is a linear function. So if I want to look at this from a more broad, a more abstract perspective, then the performance it can be characterized by some linear function, right? And by some linear function, I simply mean, say, t sub n, where t sub n is representing, say, time, is equal to a(n) plus b, right? It's some linear function. What is a? What is b? When I wrote it down up here on a piece of paper, I said we didn't care about it, right? At the end of the day, that's true. But there is some value there, a and n. A and n, however, depend on my computer. How fast is each operation? How many node traversals can you do in 1 second, right? Well, take this and upgrade the hardware to a computer twice as fast, and that a constant will go down. How much time does it take for your Java virtual machine to start up, right, or do some things in the background? That's captured by b. It's some constant amount of time or resources that doesn't depend on how many elements are actually in your list, right? It's just what the Java virtual machine needs to do to actually execute. Okay. However, with a linked list, in contrast, right, a linked list implementation, each get sub I. Oops, I wanted to code bracket that. Sorry. There we go. Each get sub I takes a linear amount of time or resources or operations, right? The loop, again, executes n times. Therefore, that's where we're getting that n squared. If I do a linear amount of operations, a linear amount of time, right? Look at this loop right here. This loop is executing n times. And in each one, I'm doing about n operations, right? That's where I'm going to get, therefore, the total amount of operations is proportional to some quadratic function. So let me just go ahead and put that down. It's a different t in this case. T sub n is going to be, I don't know, a(n) squared plus b(n) plus c, right? You've seen that equation over and over again. You've got the quadratic formula. You know, it's just it's a generic, general quadratic, right? Now, in our formal analysis, in our whiteboard analysis or white paper analysis up here, A turned out to be 1/2, B turned out to be 1/2, and C turned out to be 0 because we weren't considering anything that the actual algorithm was running. But A, B, and C are not necessarily fixed all the time. Again, it depends on the machine that you're running it on. So what I did is, let me go ahead and, here we go. What I did is I ran this over and over and over again, at least the linked list one. And I wanted to find out what A, B, and C actually were on my machine at one point in time. I think I used the same machine for this. And what I did is I came up with the following. Oops, drawing, why not? Oh, you know what? I need to copy it, sorry. It's graph.p, there we go. And bring it over here. There we go. All right, and refresh you. Come on. Okay, there we go. Come on, refresh. It's not showing up. All right, fine. I don't know why it's not being embedded here. Let me go ahead and just open it up manually. Lectures. Algorithms. There we go. I generated this, I think, with GNU plot, I think. So in an index-based linked-listed implementation. That blue line right there was the measured performance, right? And we thought, from our analysis here, we thought, oh, it looks to be probably quadratic. The red line there is an actual quadratic regression. So you've probably heard of linear regressions before. If you've got a bunch of points and it kind of looks like it follows this line, you can do a linear regression to get just a regular old linear function. Now, not all those points are going to correspond to that line, but that line is the most accurate with respect to all of the points. That gives you a value for the constant coefficient sitting out front and the constant value sitting over here when you've got a n plus b. Right? What I did here was a quadratic regression. In other words, it came up with a quadratic, an actual quadratic, not formula, but quadratic function that kind of fit this data. In fact, it's really, really, really close there. Right? And from that, I was able to pull A, B, C, and D, A, B, and C out of this, right? So from the quadratic regression, here are my coefficients. Right? It turned out to be very small coefficients, which is what you would expect because computers are fast, right? If I upgraded my hardware and reran this experiment and reran the quadratic regression, those numbers would be even smaller if there was a faster computer. If I downgraded to a slower computer, those coefficients would be larger. But it wouldn't change the overall function. The overall function would still be a quadratic function. If I go from 1 million to 10 million, I'm looking at a 100 times slowdown, 100 times more operations. Right? But those coefficients out there might change slightly, but they're going to be the same order of magnitude. From that, now that we've got those values, we can start making other more accurate predictions. Right? How long will it take to sum lists of various sizes? Right? We already did, we tried to do 1 million. 1 million was about 500 seconds, right? So what about 10 million? Oops, 10 million. How many seconds would that be? Another 100-fold, right? So if I took 500 seconds before, then it would take 500 times 100 seconds, which is about 50,000, right? 50,000 seconds is how much time? Does anybody want to do the math in the back of their hands? I'm using the actual equation up there. And so when I did that, I came out to 17.498 hours, right? Right? Versus, what was 10 million when we did an array list? There we go. Let's go ahead and run that. So 0.014 seconds versus, what was it? Almost 18 hours. All right? What if we went even further? And I'm not going to do it on my computer here. But what if I went with 100 million? What do you think it would be now? Again, I'm increasing the size by 10-fold. If it's quadratic, it's going to be 100 times slower or 100 times as much time. So 100 times 17 hours is 74.06 days. Right? If I go up to 1 billion, how much time do you think now? No? Nobody wants to venture a guess? It would take 20.32 years. Right? Now, are you going to say 1 billion? That's not big data. Right? Not even that is big data. 1 billion integers is 4 billion bytes, and 1 billion bytes is 1 gig, or less than 1 gig. So you're talking about 4 gigabytes of data being processed. Would you wait around for 20 years on that? No. Right? In contrast, I did the same analysis, by the way, for linear predictions. or for the using an array-based list, and with the same amount, I came up with the following estimates. The 10 million is about less than 1 second. We already saw that in practice here. 100 million would be about 10 seconds, and 1 billion would be about 2 minutes. They're roughly about, right? It's probably going to be even less than that. But that's my back-of-the-envelope kind of calculation. Why? Because it's linear. With a linear function, if you go from n to 10n, well, that 10 just translates out front, right? And it's 10 times slower. So if it takes you about 1 second for 10 million, then to go up to 100 million, it only takes you about 10 seconds. To go up from 100 million to a billion, it only takes you about 100 seconds, which is in the range of about 2 minutes. And that's why I say these were just estimates. Huge contrast there. Right? What's the takeaway on this? The takeaway is that quadratic algorithms are not acceptable. Right? Linear algorithms are better. And in general, if you can go ahead and analyze an algorithm and capture its behavior as a function, then now you can start talking about the relative performance of two different algorithms. This one's linear, this one's quadratic. This one is clearly the winner. This one is linear, but this one is slightly less than linear. Well, then this one is the winner, right? And if you can do that, to do that requires a formal framework in which to in which to actually analyze algorithms, right? And so that's our motivating introduction for the next week or so. And now let's give an actual introduction. Clearly, from the demonstration here, computational processes have some expense or expend or require some resources. This goes beyond just simply time. Examples would, of course, include computation or CPU time, right? What else? What are the resources that a piece of hardware like this requires? Never thought about it before? Memory, all right? Memory. What else? You walk around with your phones all the time. What's your biggest concern when you've got your phone with you? Battery life, right? So, in other words, power, right? Power consumption. What else? Again, think about your phones. You go from inside a building on UNL's campus where you're probably connected to the wireless versus you go out of town, off campus, and now you're not roaming anymore. You are on a 3G or 4G network, right? And then you go out in the maybe further away from a city, and now you don't have any, or now you only have LTE or whatever they call it, right? What is the difference between all of that? Could you watch Netflix out on an LTE network, or whatever it is, 2G, let's say, or a 0G network? Why? What resource are we talking about there? No? Signal strength, but also we could accept a weak signal as long as we can still push data through, right? So network bandwidth or throughput. Right? How much data can you actually transmit over a network? Right? There might be some electrical engineers in here. What are your concerns when you actually build a circuit? What are your resources then, other than power? What complicates the building of a circuit? You can build a very simple circuit. I forget what they're called, the resistor, transistor, the RTE, is it? What is it? Any electrical engineers yet? No? Okay. An RTE circuit or something like that. Very, very simple circuit. Or the hardware sitting inside my computer here, the processor, extremely complicated circuit. How do you build circuits? No? Gates and wires, right? If you can build one circuit that requires, or using 50 wires and 80 gates, and then you build another circuit that only requires 10 wires and 5 gates, right? This one is clearly better because it's simpler to build, fewer failure points, less power, right? and faster because you're going through you're causing less voltage changes as you go through that circuit. Anybody work with any virtualization? So virtualization would include like virtual machines. One reason that you want virtualization is because consider smaller departments on campus where maybe 10, 20 people go to their website a day or maybe a week or something like that versus UNL's main website or a website like Amazon.com, right? Now, vastly different resource requirements there, right? Do you need an entire dedicated server to serve 20 web 20 web requests per day for a small departmental website? Do you need dedicated hardware, $10,000 server to do that? No. Instead, what you can do is you can buy one $5,000 server, whatever it would be, and put 10, 15, 100 virtual machines on it. Each virtual machine is serving a different website, right? But they're all running on the same machine. Imagine we didn't do that. Imagine that we did buy this $5,000, $10,000 machine, and it's only serving a small contingent, like 20 people a day. What is it doing for the rest of its time? It's just sitting there, right? We call that idleness. So idleness, or utilization, right? That's another resource that you can think of because we put $5,000 into that machine when we could have bought simply a $20 a month virtual machine from Amazon Web Services or whatever, right? So it's wasted sunk cost, right? So another resource measure is, well, at the end of the day, all resource measures are money, right? All of these things cost money. Time is money, power is money, idleness or wasted resources are also money, right? But do we really care about these things with respect to an algorithm? Remember, those constants sitting out front, if we upgrade our hardware, they become smaller. If we downgrade our hardware, they become larger, right? The above are extremely, extremely important engineering considerations. If you were designing and building an embedded system of some sort, extremely, there we go, important engineering considerations. If you were building an actual piece of hardware, if you were building an actual embedded system, then yes, those things become very, very important. If you're building a real-time system, then the responsiveness becomes super important because if you are building a real-time system to keep glider control for a UAV vehicle or something like that, then that it has to respond to changes in air pressure very, very quickly, right? So those constants then start to matter. If you can increase the response time by tenfold, absolutely, you invest your time and effort into doing that. But from an algorithmic point of view, they are all just constants that do not matter, right? Meaning that, again, if you go from a piece of crap hardware and upgrade that to twice as fast, those constants go down, but does that n squared change? Does that n change? No. That's the nature of the algorithm itself. From an algorithmic point of view, we are interested in the inherent nature of the algorithm itself, right? We don't care about those constants. We want to define the behavior of it. Is it a linear algorithm? Is it a quadratic algorithm? Is it an even more expensive, exponential algorithm? Or is it a super cheap constant algorithm, right? Those are the best, right? Because then it doesn't matter how much input you give it. It executes immediately, right? The reason for this is that algorithms exist independent of computers, right? How old do you think algorithms actually are? So the first electronic computers are within the last 60, 70, 80 years, let's say. Do you think that the algorithms were born 80 years ago? Thousands of years old. Euclid's algorithm goes back to antiquity, 600 BC or something like that. I don't remember off the top of my head, right? That algorithms have predate modern computing by centuries, or actually millennia, right? The first person to take 2 and 2 and add them together, they were performing an algorithm, right? They were doing addition, 1, 2, and then 3, 4. That was the first algorithm probably, right? Adding 2 things together. They're very, very old. An algorithm does not suddenly become more efficient with better hardware or less efficient with worse hardware. It just is. It has an inherent nature of how it performs. Instead, the amount of data that you can handle in a fixed amount of time increases. Or, saying it another way, to handle the same amount of data takes less time with faster hardware. All of those are great engineering considerations, but they are not algorithmic considerations, right? An algorithm, instead, is an abstract process, is a description of an abstract process, right? It requires a language to describe it, right? Let me go back to Eclipse here, right? This is kind of an algorithm, but it's not really. What is it? What is that thing there on lines 9 through 15? It's a Java method, right? That's not necessary. That's an implementation of an algorithm. If I rewrote this for, say, C or Python or whatever, right? It would be the same algorithm, but it would be in a different language. It would be a different implementation of that algorithm. So we don't want to describe our algorithms as Java code. We don't want to describe our algorithms as Python code or C code or whatever, because again, algorithms existed thousands and thousands of years ago, right? Java has only existed in the last 20 or 25 years. Algorithms weren't suddenly birthed by somebody creating Java, right? So instead what we need is we can describe an algorithm using pseudocode, right? Fake code, not Java code, not C code, et cetera, et cetera. Instead, it's pseudocode, right? It's pseudo being Greek or Latin, I don't know what, probably Latin for fake, so fake code. Again, the formal definition here is that kind of like the dictionary definition. Let me spell this correctly. Instructions. There we go. That's the dictionary definition, which is good enough for this class. That's nowhere near the real definition of what an algorithm is, right? The real definition is a mathematical definition, and it's not really even it is a definition. It's called a Turing machine, right? Equivalent to that would be lambda calculus or something else like that, right? Or a grammar or something. We're not going to get into Turing machines, but this is a good enough definition for us to work with here, right? An algorithm is an unambiguous sequence of instructions for solving a problem. An algorithm is not Java code. It's not a method. It's not a function. It's not a snippet of code in a particular programming language. Instead, we need to use pseudocode to describe an algorithm. Right? We'll use a pseudocode, excuse me. There we go. All right. What is pseudocode? Well, guess what? There are no rules. Right? If there were rules for writing pseudocode, guess what you have? It's called a programming language, right? And you would have Java code, you would have Python, you would have C, whatever. All of those things are simply just codifications of rules and languages in order to actually get a compiler to understand it so that it can compile it for machine code. If there were hard and fast rules for pseudocode, it would not be pseudocode. Instead, there are general guidelines that you should follow when you're writing pseudocode. It makes use of plain English, or capital English, right? Makes use of mathematical notation, right? Doesn't use language specific, and this is programming language specific, syntax or constructs, right? In other words, it would be wrong in pseudocode to say, well, I've got this math class and math.square root, whatever, right? If you want the square root, we've got a mathematical symbol for that. You write the radical there. You write square root instead, right? It gives essential details of the process while omitting any unnecessary details, right? And we'll look at a couple of examples here to understand what I'm talking about. But basically, it's not it's Goldilocks, right? It's not too short, it's not too long, it's just right? It's right in the center there. You don't want it. You don't want it. You don't want it too hot. You don't want it too cold. You want it just right. And how do you know that it's just right? You don't until it's more art than engineering, right? But there are some extremes in which you can say, no, that's way too specific. For example, if I start pulling out Java maps and saying, okay, then I'll go ahead and get the key set out of that, and then I'll dump the key set into a constructor so that I can do this and this and this, that's way too specific. That's way too language specific. On the other extreme, if I ask for an algorithm that describes how to sort a collection of elements, and you just have a one-liner that says sort them, right? That's way too terse, right? You want something in between. You want something like, say, selection sort, which we'll look at here in a moment, right? Again, they're just guidelines. I can't give you rules. If I gave you rules, guess what? I just wrote a programming language, right? Instead, we'll look by example, right? And actually, the rules that I'm going to follow here are nothing more than the LaTeX, the way that there's a LaTeX package that I write everything. I write everything in LaTeX. It's a typesetting language, and so I use a package called algorithm2e, and I've got it to look nice. And so that's the style that I've adopted. It's not the only style there is. As long as you're following a consistent styling, you can write your pseudocode however you want. So let me go ahead and go back to my doccam here. Doccam. There we go. All right. And before I went on, we're going to look at two examples. One of them is going to be finding the maximum element in a collection. Okay? So we're going to write pseudocode here on a piece of paper because, again, I'm going to be using mathematical notation. I'm going to be using some plain English. I'm going to be doing some indentation and stuff like that, and I'm not going to be able to do that with the overhead projector that I've been using. I've been writing over here in Markdown. Markdown does. I could go into code mode, but then it would just look like code, and I don't want it to look like code. Okay, so the first algorithm is given. Now, if this were C, or Java or whatever, if I gave you an array, then I would expect the public static int get max, and then you took an array, and if it's C, then also the size of the array, and the return type is integer because I want you to go through that array and find the maximum element. So you'd have a for loop. You'd have like the current max variable, then you'd have a for loop that iterates through, and an if condition. If array sub I is greater than the max element so far, update the max element, and then finally a return statement down here that says return that value. I don't want to think in that, right? It's going to look very similar, but the actual pseudocode is going to be looking very, very different. Now, we do want to clearly label our inputs and our outputs. You can even give it a name, right? I can give this a name of find max. Right? I'm going to label the inputs. Well, what are the inputs in this case? Is it an array of integers? What does that sound like? An array. That's code specific. There are languages that don't have arrays in the traditional sense. PHP, for example. PHP does not have arrays. They have associative arrays, which are basically just neutered maps. Right? Not all languages. Some languages will have arrays, but then they don't have to be zero indexed. Right? Some languages, well, a lot of languages do have arrays, but that's a language thing. This is pseudocode. So what I want is a collection, A, and I'm going to give it a name, A1, A2, dot, 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 AN, of, now, here's a good question. Even in Java, would you say that you want to implement getMax using only integers? So should I say that this is a collection of integers? That seems way too specific. Elements, right? Why is that way too specific? Even if this is Java, that would be way too way too specific. Why? When we made a stack, when we made a queue, initially we made them at a stack of integers. What did I do as a final step? I changed it so that it would be a stack of elements of type T, generic, polymorphism, right? So that you can write one piece of code that finds the maximum element in any collection of anything, right? So even in Java, that would be way too specific, and we would never do something like that. A collection of elements, I've given it a name. Not only have I given it a name, but I've given the elements in that collection, maybe with a comma here, names as well. And what else have I told you? The last one has an index, the first one has an index of 1, the last one has an index of n. That tells you how many elements are in that collection. Right? If this were C, you would have to pass that in as a secondary value, right? You have to pass in the pointer to the array and also the size of the array. If this were Java, you wouldn't need to do that because you've got .length. If this were Python or PHP, you've got a function that will allow you to do that, count, right? Those are how languages do it. This is how I'm going to do it with pseudocode. A collection A of elements, right? That's as generic as it gets. I didn't say array, I didn't say set, I didn't say map, I said a collection, right? The output will be the maximal element x in A, right? Now, why did I go with maximal here? What if the collection contained 1, 2, 3, 4, 5, and then another 5? Technically, is there a maximum there? No, because it has multiplicity. There are 2 5s in there. So I'll say maximal element because will you give me the first 5 or the second 5 or the middle 5? I don't know. That's on you. That's for you in your implementation to describe that. For me, this is just pseudocode, the maximal element. Okay. Now we need to start writing our actual pseudocode. So let me go ahead and create a max element. Right? And I can set it to the first element, right? A1, say. That's how you might initialize it in a piece of code. In a piece of code, how would I assign this value to this variable over here? Equals, right? The single equals sign. Now, there are lots of people, or I read an article a long time ago that was lamenting the fact that they did it way back when and used a single equal sign for an assignment operator. It never should have been that way because that is a violation of algebra. Algebra, you've got a single equal sign. A is equal to B. That's algebra. So what did we have to do in code to rectify that? We had to add another equal sign, equals equals. And then in programming languages like PHP or JavaScript, there's an equals equals equals. Right? That's a strict equality testing rather than just loose equality testing with 2 equal signs. So adding more and more and more equal signs to get different meanings of the equal sign, it seems like it was a mistake 40, 50 years ago when they started doing it. I have no opinion one way or the other. But in our pseudocode here, we're not going to do that because there are languages that don't use the single equal sign as an assignment operator. Does anybody know of any? R. R uses colon equals?
I think R actually uses like arrows.
Oh, okay. That's what I'm going to use. But in R, it's going to be a less than sign and then a hyphen to get that arrow, right? I'm assigning this value to this variable over here, right? R does that. I think Haskell might do that. I'm not sure. Another programming language called Maple. Right? Do you guys use Maple in your calc courses still? No? Okay. Maple uses a colon and then an equals. I think that's inspired from either COBOL or old school Fortran or something like that. I'm not going to be that specific. I'm just going to use this arrow here. Put this thing into that thing over there. All right? So I've initialized it to the max. Now I can have a for loop or a for each element. Let's say a sub I in A. And then I can describe what I'm going to do in that for loop. For each, I'm using a combination here of plain old English along with mathematical notation. I put in here, generally if you've had 235, I would put something like this instead, right? That's the membership symbol, right? This element is in this set over here, or in this collection over here. I'll go ahead and put that in parentheses up there to describe it, though. So for each element, I'm going to make a check. If a sub I is greater than max, then I will update max to be a sub I. Right? Now, this looks very Python-y with this colon right here. I regret doing that. I just did that out of habit. If I had some white out, I would take it and remove that. But I'm also using indentation here, which is perfectly fine. But I'm not using, I'd rather not use the colon there. If this were C or Java or a C-style syntax language, you would use an opening bracket and a closing bracket. Opening bracket here, closing bracket down here, opening bracket here, closing bracket down here. Instead, what I'm going to use is these things over here. Right? It's just a vertical line showing you where this block ends. Right? There is no way for you to get that in a Markdown or Java or something like that where you've got a plain text editor. That's why I like it, because it drives home the point that this is pseudocode. There's no way to typeset this unless you use LaTeX, right? And that's what I use. Right? And then, as a final step here, we've found our max after this for loop. What should we do? Should we return max? Return. Does that sound right? Return is what? That's a keyword in Java, C, et cetera, right? I'm just going to, well, what are we doing? We're giving you input. We're giving you output. So I'm simply going to output it. Output max. There. Now, there are variations on this. If you ask somebody else to write pseudocode for the same algorithm, they might come up with something slightly different, right? They might start at, like initialize this to another variable. For example, let me go ahead and edit this, right? Since we're already comparing everything in the collection, what could we initialize max to? We could initialize it to null. Null's way too language specific. What is guaranteed to be greater than anything else? Negative infinity, right? Now, the first time that you get to an actual element, it's going to be greater than negative infinity, so you end up initializing it down here. Like I said, you can liberally use as much mathematical notation as you need, as you want, right? Again, I avoided this because I don't know if you've had set theory yet, right? And you might get other variations as well. Like, for example, here, if a sub I is greater than max, we didn't say what these things were, right? We didn't say that these were integers. They could have been accounts, or they could have been invoices, or they could have been products. What does it mean for one product to be greater than the other? I don't know, right? I don't even know that these are products. They're elements, right? Those kind of questions come into play when you actually need to implement this algorithm, right? And then you'd use a comparator in Java, right? Good. What was the other one? Was it selection sort? Oh, the mean of a collection. Okay. So, compute mean. Right? And we're good on time. So help me out here. Right along with me. What's the first thing I should do? Probably identify the input and the output. Right? So what's the input here? A collection. Give it a name, give the elements a name. of elements, right? And here you could say of numbers, right? Or whatever you want, right? And the output will be the mean of A, right? Okay. Help me out now. To compute a mean, what would you do? The average, right? All right, add up all the elements, right? So I need a variable to contain the total, right? So total. What should I initialize it to? 0, all right. For each, and you could say a sub I in A, total. Now, if this was C, Java, whatever, you'd be using a compound assignment operator. So plus equals, right? I don't have that luxury here. I'll have to go with longhand. Total plus A sub I. Okay? That's the end of my for loop. Now what do? I can go ahead and assign another variable. All right? This will be total, and then a divide by what? Now I'm even getting bad habits. There we go. I can write fractions, right? I can write, because this is just free form and this is mathematical notation, I can write proper fractions rather than using the forward slash or the symbol, right? Now, what symbol is usually used to denote the mean in math? We know how to write it, but do we know what it is? No? All right, nobody is up on their Greek. Mu, right? Right? I think so. And we can output it, finally. Output mu. Right? And there's my algorithm to compute the mean. Again, using mathematical notation, common mathematical notation here for mu. Initialization using an assignment operator, right? Addition, that's standard enough. And being as generic and as abstract as you can. If I gave this pseudocode to you and you were a Java programmer, you all are Java programmers, you could implement this in Java. If I took this and gave it to an R programmer, they could implement this understanding the algorithm, right? So that's the point of pseudocode, to be as generic and general as possible. Let's go back to HTML. There we go. All right. So once we've got our pseudocode and our way to describe something, we now need to analyze it, right? I'm not sure where this came from. I think it's probably from when I learned it and modifications over the years. But I like to give a 5-step process. That 5-step process, I like people to follow it because then they don't miss a step, and it allows you to focus on one thing and one thing only before moving on to the next step. So to analyze an algorithm, and like we did at the beginning and said, oh, this algorithm looks like it has a quadratic performance, whereas this algorithm looks like it has linear performance, right? Rather than running that experiment and coming up with, there it is. Rather than running the experiment a bunch of times, thinking, oh, it looks like it's quadratic, and then doing a regression to see, oh yeah, it definitely is quadratic. You want to look at it from a theoretical point of view. And so to do that, I like to give you a 5-step process. The first step is to identify the input. Well, guess what? That's already done for you if you've written correct pseudocode. Right? Step 2, identify the input size. Right? And again, that's usually done for you, but there are, done in the step of actually writing the pseudocode, but there are some tricks there, and I'll identify them as we go along. Identify what is called the elementary operation. Right? Operation. There we go. And this step is we've already seen the importance of this step. When we looked at summing up a bunch of things in the using a linked list, I identified 2 operations: a sum operation and then a node traversal operation. And if I went with one or the other, I would get a different impression of that algorithm. If I just went with the sums, I would say, oh, this looks linear. And then when I run it, and it takes 20 years to actually execute, it looks like I'm wrong, right? Instead, what you wanted to focus on is the most common or most expensive operation in the algorithm itself. Right? And that's why I put this as step 3. And that's what an elementary operation is. You need to determine, step 4, how many times the elementary operation is executed with respect to the input size. All right? In other words, you come up with a function. You can say t sub n, where n is the input size. Right? And you want to come up with this function because that's what we did in the beginning. This thing is linear. This thing is quadratic. Clearly, linear is better than quadratic. And only after you've come up with a function that describes the behavior, the growth rate, etc., that's when you can start to say, oh, this algorithm is definitely going to be better. This algorithm is probably not going to be as good. Right? And then 5, as a final step, you can characterize the algorithm's behavior using asymptotic, that is, big O analysis. And that's what we'll eventually get to probably next week. Right? Instead, what I'm going to do in the last 15 minutes here is we're going to go one by one, right? In each of these steps. And then we won't have time probably, but we will have time next week to go through an example of the first 4 steps. So step 1, identifying the input. As I said before, it's generally already given as part of good pseudocode. If you write good pseudocode, then you've already identified the input and anything else that you need to identify the input. However, there are some corner cases. For example, in some cases, there may be multiple inputs. Right? So, for example, instead of computing the mean, linear search. All right? You've got a collection and you've got a key. Find the element in that collection that matches the key. Right? Here's an array of integers. Search through it and tell me if 10 exists in that array. Right? Just a basic search. There's actually 2 inputs there. Right? There's an array, and then there's the key. Which one is more important with respect to that algorithm, at least? Which one would you look at instead? Would you look at the thing that, well, there's only one of them? Or would you look at the thing there where there could be 100,000 of them? Or 10 million of them? Which one that you're actually going to be traversing through? Which one of those things is more important? Probably the one over here that can actually grow. There's only ever going to be one key over here, right? So, for example, example, searching an array for a particular key. Right? The size of the array is more important. So you always whittle it down to only one, right? In some other examples, for example, Euclid's GCD algorithm takes 2 integers, right? A and B, right? And then you need to find the greatest common divisor of both of them. I don't have an example off the top of my head. Well, I could do an easy example, 2 things that are coprime. 3 and 12. What's the GCD of 3 and 12? They're not coprime, so that's easy. It's going to be 3, right? 3 divides 3, 3 divides 12, and there's nothing larger that divides 3 and 12 at the same time. All you need to do is iterated division to do this. Again, this is a very old algorithm, 2,400 years old or something like that. And it takes 2 integers, right? So without loss of generality, right? Here's a fancy way of doing that with wlog, right? This is without loss of generality, right? Choose the larger of the 2, and I'll put that in quotes here because we don't know what larger means yet. Larger of the 2 inputs, right? And so let's just say that A is larger than B, right? If they're not, then in your algorithm, all you have to do is switch them around, right? You can have a real simple if statement if you're really that worried about it. But we'll just say that A is larger than B, so A is our input. Why does that not matter? What if you really wanted to take both of those inputs and consider them both? So here's A. Say that it takes, say, 10 digits. And here's B, and it takes 20 digits. Right? So you want your input size to be 30 digits. Right? But 20 digits, 10 digits, 30 digits, it doesn't really matter. Right? What you can do is you can take this 10-digit number, and you can expand it out into 20 digits by putting 10 zeros in front of it. Right? And now it's a 20-digit number with the same value. Right? You wouldn't do that in practice, but you can see that now a 10-digit number and a 20-digit number, now they have an equal size. Generalize that. Now say that this has n digits and this one has n digits. Right? So together they have 2n digits. Do we care about that 2? Where's that 2 going to end up in our equation, our t sub n equation? It's going to end up out front as a coefficient, which we're ultimately going to ignore. We don't care about that. The coefficients, they can go down with better hardware. They can go up with worse hardware. They're not that important. The n's are important. The growth rate of those functions are important. Okay? So without loss of generality, you can just go ahead and say, choose that one right there. To simplify your analysis, you only want one input. Right? You can also get in trouble with input sizes, even though it looks like it's simple. Right? It's subtle, but important, and may be tricky. Right? For certain things, like if your input is a collection, then it's the size of the collection. Right? Collection. Right? What other types of inputs have you encountered so far? List and arrays, those are collections, so that would fall under there. What other things have you processed so far? What about last semester, an image, right, where you went through and you changed the RGB values to sepia tone or something like that? Right? What's your input size there? That's not really, it's still kind of a collection. If I've got an image that's I don't know, 1,000 pixels by 500 pixels, then how big is my input? 500,000 pixels, right? So it would be the number of rows, or the dimensions, times the columns. Right? So you could look at that, look at it from, say, an image. It's going to be the height times the width, right? So in other words, the number of total pixels. Right? What if it's just a number? Right? Say an integer x in, let's see if we can do this. So, oh, hey, it works. Cool. All right. So again, mathematical notation. If you haven't had 235, that's fine. It's not going to be needed here. X is an integer. That fancy z there is the set of all integers. So 0, 1, 2, 3, 4, and also -1, -2, -3, -4, all in both directions. Right? What about a number? What's the size of a number? This will probably be the last thing today, so I'm going to go ahead and move over to the dot cam. We're going to do some math. All right. So here's my number, 1,734,832. Right? What's the size? This is n. What is the size of n? Right? And again, you have a number as input. You could find the largest the largest prime number, or test it is prime or composite, or test what is the largest prime divisor of this number, or factor it completely, or something else. It's just one number, right? What is its size? Is its size 1,734,832? Did it take me that many symbols to write down? No. What's its size? Yeah, its size is 7, right? And what do we mean by 7? It takes 7 digits to represent. Right? Take another number, maybe only 780. right? You would say that this number is larger and it has a larger size, right? And that this number is smaller and therefore has a smaller size. What is its size? It's only 3. Right? It's not an order of magnitude larger, or this 1.7 million is not an order of magnitude larger. It's the number of symbols required to write it down, right? Now, you could go way back to the Romans and an extremely inefficient numeric system. How do I write down 1? I. How do I write down 2? I. 3. I. And 4. I, V. Now it's only 2 symbols, right? So what's their size now? Size is proportional to this number over here, right? That's not how we work. That's not how a computer works, okay? So if I gave you n, then what is the size of n, right? If I gave you 9, then what's its size? How many symbols did it require for me to write down to represent? 1, right? What if I gave you 99? What's its size? 2. What if I gave you 999? 3, ... What if I just gave you a power of 10, right? Let me rewrite this. 10 to the n. No, I don't want that. How do I want to do this? What if I just gave you n? Right? What's its size? Well, it was easy to work from this direction to that direction. What I'm asking you to do now is work from this direction to this direction. Right? So what's the pattern? Forget this for a second. What's the pattern over here? If I gave you this many digits to work with, if I gave you 1 digit, what's the maximum value that you can represent? 9. What if I gave you 2 digits? The maximum value you can represent is 99, ... What if I gave you k digits? What's the maximum value that you can represent? What's the pattern here? 10 to the k minus 1, right? Now, say that this is n. 10 to the k minus 1. Now let's work back forward over here. If this is n, then what's my k? All I need to do is solve for k here. Right? So let's do that. N plus 1 is equal to 10 to the k. Now, how do I get that k alone? What? Log. Log base what? 10, because that's my base right here. And now I've got k. Okay? So, given n, right, what's the size of it? It's this thing right here. Now, I only worked in 10. Why? Because we humans have 10 fingers and 10 toes. Is that how computers work? Nope. How do computers work? Log base 2, in base 2. So if I gave you the same exercise here, if I gave you 1, not digit, but if I gave you 1, they are called bidgets, by the way, right? But we've shortened that to bits, right? Because that sounds stupid, right? All right, what's the largest number that you can represent over here? If I gave you 1 bit, you can represent either 0 or 1. Which one's the largest? 1. If I gave you 2 bits, what's the largest value that you can represent? 1, 1, which in base 10, to understand it, because we're just human, what is that? 3. If I gave you 3 bits, then the maximum value is 111, which is equal to 7. 4, you see the pattern here, 1111. What is that in binary? 15. If I gave you ... if I gave you k bits, then you could represent 111 ... 11. There are k ones here. What value is that? 2 to the k minus 1. Right? The only difference from what we looked at before was what? The base. Right? now you can see that all bases are the same to within a constant, right? It doesn't matter that you have 10 fingers and 10 toes. That computers only have one finger and two fingers, or 2 fingers and toes, or if you want to think of it that way. It doesn't matter that you represent stuff in octal. It doesn't matter if you represent